Hey Trevor, hope you're well. I heard you're looking for software to do statistical tests on data and you're thinking of using SPSS, which is also good, but I want to tell you about our program. It's another option with cool features and I'll teach some. First, it's open source. You can ask for help from the user community and it's free for everyone. It's more comprehensive statistical platform in simple words. It's like a one-stop shop for all your data analysis needs. And you can use various types of data such as text, DBMS, Excel, so on and so forth. You can also use to find patterns between the data. For example, you can use this to find out simple things like to see if people who buy one product are likely to buy another. It can operate on various systems like Mac, Windows, Linux, and then it helps you understand the information from data analysis with pictures and graphs. For example, it can show relationships between many different data in a single graph or a chart. And another one feature is like in order you write instructions and scripts to do complicated data analysis. If you have the same data in the future, you don't have to start from scratch. You can reuse the same instructions or modify them to analyze the data. And R has a large global community of users. All people around the world use it. They share tips online and help each other solving problems. So it's very convenient to use. On Google, and you will be lead to this page, and then click install R on the left side, and then click download R, and then click this one, and then this one, and then if you open file on your computer, and then follow the instructions, and then when you finish, when you click finish, and your program is already downloaded on your computer, and you can start writing script and open it on our program. So I will export my file to R Studio. So here is my file. Oh, it's already exported. Here, the script, and then select all, and if you run it, actually it shows so the data is already exported. To view it, so here the file name is this one. So to get the dirty data, you have to the maker, and then insert the number of data that you want, and then run it. So actually it's the data is already imported. So to view it, you write the file name again and then run it. So here you can view the data. You can also view from the table. And then to show how to export it as an Excel spreadsheet, the script that you have to write is write CSV, and then the file name, so which is the fgen in this case, and then the name that you want to name your file, so the fgen 30 ECC, and then add CSV here, and then row names true. I will explain it on the Excel file for this, so when I run it, and then actually the dataset is already exported to your Excel file, and then you need to open it from the file that you set your directory in your R program. So this is my file location, and it's here, the UFGen 30 VCC. And if you open it, so it's already exported to Excel. So a t-test is a type of statistical test that is used to compare the means of two groups to see if they're significantly different from each other. There are two types of t-tests, independent t-test and paired sample t-test. An independent t-test is used when we want to compare the means of two independent groups to see if they're significantly different. For example, height of the men and women. And then paired t-test is used when we want to compare the mean of the same group at two different times, like comparing before and after treatment. And then I will conduct a paired t-test on the same randomized data. Since it's paired, so I'm using two same group but two different times. So I use the time one with the people with allergy and the time two with people with allergy. And then to get the data with allergy, I need to make a substrate. So I make it this, so it's here. So allergy, yes. And to get the substrate, subset. And then the data is the name, the F10, and then the variable that I want to use is allergy. And then it's yes. Okay, and then so I already get this data set for the people with allergy already. And you can only run t-tests if the two data sets are normally distributed. So to check the normal distributivity of the data set, we use Shapiro test. So is the data set is yes, and then we're comparing time one. So and then run it. So here the p-value is larger than 0.57, so it's larger than 0.05. So it's normal. So we do the same for the time two. And then run it. Oh, the p-value is also larger than 0.05, so it's normal. Since both data sets are normal, now we can run the t-test. The script for t-test is t-test, so we're comparing yes, time one, and then yes, time two. Since we're doing paired t-test, paired, and then write true, then run it. So we got the results for paired t-test, and if you see the p-value, which is very much larger than 0.05, so we can accept the null hypothesis. If we want to determine if there are any significant differences between the means of two or more groups, we can use ANOVA tests. There's one-way ANOVA tests and two-way ANOVA tests. A one-way ANOVA test has only one independent variable. For example, let's say you have three types of different balls, and you want to know if one type of ball bounces higher than the others on average, and the types of the ball is your independent variable, and the height of the bounce is your dependent variable. And for two-way ANOVA tests, let's say you also want to know if the surface you're bouncing the ball on makes a difference on how high the ball bounces, and you also want to know if certain types of balls bounce higher than on one surface compared to the other. In this case, you have two independent variables, types of the balls and types of the surface, and one independent variable, height of the bounce. I will run one-way ANOVA test, and my hypothesis for changes is the significant effect of ethnicity on the score. So ethnicity here is the independence variable, and score is the dependence variable. So I will make a subset for each ethnicity here. There are a few assumptions before you have to do before running our ANOVA test. They're testing normality, so we will use superior test to test the normality here. Since the data sets are normally distributed, we can now run an ANOVA test. And before to run ANOVA test, there's one thing we need to do is to convert the characteristic variables into numbers. And here is if you check here, it's converted into numbers. And then there's another assumption we have to do is equivariance. To test variance, we will run 11 tests. Before we run 11 tests, we need to install library card package. Okay. Now we can run 11 tests. Here it's larger than 0.0.5, so there equivariance. Now we can run ANOVA test. So ANOVA test is result. So here 0.6, so it's larger than 0.05. So we can accept the null hypothesis, which is there's no significant effect of ethnicities on the score. Way to see if there is a correlation between the two datasets. It's important to note that here correlation does not imply causation. Just because one variable, two variables are correlated, does not mean like the changes in one variable is causing changes in another variable. And then there's several types of correlation tests such as Pearson correlation and Spearman correlation. Both Pearson's and Spearman correlations are ways to examine the link between the two datasets. Pearson's correlation is a test that is used to see if there's a direct connection between the two datasets. It checks to see if one thing changes, the other also changes or not. This method is best when the data is normally distributed. Spearman correlation, this test is used when the connection is directly correlated or when the data is not normally distributed, instead of looking at the actual data, it ranks it and then sees if the ranks of one thing increase or decrease along with the ranks of the other thing. I will do a correlation test here to know which correlation test to use. We will test the normality on the data sets, and my hypothesis question is there a statistically significant relationship between age and income? So that I will test the normality. I will use the superior test. Since one of the data sets is not normal, so I will have to use Spearman's correlation. So Spearman's correlation. If you compare with this criteria chart, interpretation chart, we can conclude that. So that is used to make specific assumptions about parameters of the data, such as mean and deviation. The key assumptions are normal distribution, independence, variance, and data measurement. If the assumption of the parametric test is violated, example, the data is not normally distributed, in this case, we can use non-parametric test. In parametric test, the data is normally distributed, while in parametric test, the data is not normally distributed. The data of parametric are usually interval or ratio data, and then parametric tests use nominal or ordinal data. Parametric tests are often affected by outliers, and then parametric tests are more robust against outliers. The advantage of parametric tests is that they are generally more powerful compared to non-parametric tests. Examples of parametric tests are t-test, ANOVA test, and non-parametric tests. They have weight close test, Manfred U test, and critical Wayla's test. I will run a non-parametric test here, and my research hypothesis question is the mean of time 3 with the group treat is equal to the mean of time 3 with the group control? First, I will make subsets for each data set. And then I will test for assumption normality using superior test. Since one of the data sets is not normal, so we cannot run t-test, and we have to use non-parametric test, which is weight close test. Cox test, and the script is and since the data is not paired, and we don't need the exact value, since it's larger than 0.05, so we can conclude that there is no significant difference. We can accept the null hypothesis. So the mean of time 3 with the group treat is equal to the mean of time 3 with the group. This is the aesthetic mappings for variables plotted on x-axis and y-axis. Now I will run ggplot. So we look at whether age and income are linked, and the results for root connection show that income slightly increases as the age increases, but the effect is really small. Our graph shows it too. The points are all over the place, which means we cannot predict a linear correlation between age and income. I will make a graph out of this research question. I will now run the ggplot. So if you look at the graph here, the red line time 2 and the blue line time 1 resemble each other, and my hypothesis also is the means are equal, so we can conclude that there is no significant difference between the two datasets. I will show you one function in R that I find very useful and interesting is Google Sheet package. Not only you can bring an Excel file to our program, you can also bring a Google Sheet files to R, and you can always get the up-to-date data from Google Sheets in R Studio, even if the file is shared with or edited by many people. So first, we need to install packages named Google Sheets 4. And it's from ARTH. And at your email, you can bring the data now. Read sheet, and then add the file link and run it. Okay, now print the dataset. Okay, so here the data is imported to our program. Cool, is it? And there are lots of free add-ons for different analysis stats. It's great for playing with data, making charts, and doing stats. Plus, you can repeat your work perfectly. So give R a try. It's worth it.